One of the things we know about carbon from drawing its Lewis structure is that carbon always forms four bonds. Carbon never has lone pairs, and carbon is also one of the few compounds that can bond to itself. What this means is carbon can actually create compounds that are very long chains, that form rings, that form really complex structures, and have a huge amount of variety in them. Because of this variety in compounds, it actually means that some carbon compounds have the same molecular formula but end up with different structures. For example, C6H14 could mean a huge variety of different compounds. And so organic chemistry actually has a really intricate naming system. And this is so that we can always know the exact compound that we're working with. And that is the naming system I want to introduce you to today. The first thing you need to know about this naming system is it's really based on prefixes and suffixes. And the initial prefix that we are going to learn is the prefix related to the amount of carbons in a molecule. So one of the things that we do with a carbon compound is find the longest continuous chain of carbons. However many carbons make up that longest continuous chain determines what prefix we put in front of the name. So if there's only one carbon in that compound, we use the prefix meth. If there are two carbons making up a chain in that compound, we put eth. If there are three carbons in a row in the compound, we put prop. 4 is bute, and then we go pent, hex, hept, oct, non, and dec. This prefix is then coupled with a suffix that tells us about the bonding in the molecule. And so we're right now going to look at the simplest kind of bonding, and that is when the carbons are only single bonded to each other. Having only single bonds between carbons creates a compound that's called an alkane. And so let's take a look at how we would end up naming those. So we're looking at a compound that has the formula C2H6. Now, it's important to understand as well, in organic chemistry, we actually have multiple ways of showing a compound's formula. And so what I have just drawn here would be called the molecular formula. It is kind of the standard formula that we would be used to seeing, where we just have each element and how many of each element. But there are other ways that we can do this. And to show you, I wanted to show you what is called the structural formula. And this is sometimes called a display formula. Really, it shows all of the bonding and all of the elements. So we have two carbons, each bonded to each other. And they are bonded with only a single bond, and they are going to have their other bonds, because remember, carbon needs to have 4, all filled out with hydrogens. So this really gives you an idea about the actual structure of this molecule. But sometimes this may be a little more than people want to write. And so sometimes people will create what is called the condensed structural formula. And the condensed structural formula has the purpose of showing each carbon and what it is directly bonded to. So in this case, we would go C, and then we count up how many H's are around it, and we would go CH3. What we're really doing is just representing this carbon and what it's connected to. And then we would say it is also connected to a C, also with 3 H's. So this would be my condensed structural formula. Now, I'm going to show you something else, and that is called, what I call anyway, the stick formula. And really, this is a formula that is only showing the bonds, really. And it's meant for people who really know organic chemistry quite well, because it leaves a lot of information out so that people can just fill in the gaps on their own. The stick formula for this would actually just be like that. What we're really representing here is at the end of each line, and later on when we get to more like larger formulas that maybe look like this, each vertex, what we're really saying is there is a carbon at this point. So I'm going to redraw it over a little bit on this side. And what I'm really saying is at one side, there is a carbon. At the other side, there is a carbon. And since we know that carbon has to form 4 bonds, since there is only one bond connecting those two, we just assume it's filled out with hydrogens because that's the only other thing that there would be. So it's a really simplified formula, and it makes it way faster and easier to draw. Now, we should probably talk about how to name this thing. In organic chemistry, there is only ever one way to name a molecule. And so this molecule has 2 carbons that make up the longest chain, and that means we use the prefix ETH or F. And because there's only a single bond connecting the 2 carbons, it means we use the ending ANE. And so this is how we write the name for something that is an alkane. So now that we've had a chance to see how to do that, we're going to do that again, but we're going to do this for a different example. So we're going to find the molecular formula, the structural display formula, the condensed formula, and the stick formula, and we are also going to find out the name of this molecule. Now, I'm going to give you one of these, and we're going to work our way through it. So we are going to work through butane. So that's the compound we're working with. Now, for me, it's probably easiest to start with the most comprehensive one and use the structural or the display formula. So let's break down what this word means. But means 4 carbons in the longest chain, and ANE means single bonded carbons. Now, I know right now we probably don't need to write everything out, but as we get to really complex, really long names with a lot of pieces to them, I find this kind of helps. The name in organic chemistry always tells a story, and so it's important to understand the pieces of that before you start building your structure. So I'm going to have 4 carbons, and they're all going to be single bonded together. And I always like to start with that, start with my backbone. Now, because I'm dealing with an alkane, they only have the single bonds, and because it's carbon, every carbon needs to have 4 bonds surrounding it. And since there's no information about any other element, that means those other bonds have to be hydrogens. So everything is bonding to a hydrogen. Now, if we want to write our condensed formula, we're going to write what's with each carbon. So the first carbon is CH3 carbon with 3 hydrogens. Our next one is CH2 carbon with just the 2 attached. Our next one, CH2, and finally CH3. And there's my condensed formula. Now, molecular formula, I have 1, 2, 3, 4 carbons. And if we count it out, I'm going to have 10 hydrogens. H10. That's a 10, I know, that's a little tough to see there. Okay. Now, the last thing is that stick formula. And so the stick formula, start and put your pencil down and count that as 1 carbon. So 1 carbon, draw a line, 2 carbons, draw a line, 3 carbons, draw a line, 4 carbons. And so this is how I get my 4 carbons, 1 at each point and 1 at each end. And we just assume everything else is filled in with hydrogens. Now, if you're wondering why I drew it in this zigzag pattern, it's because based on the bond angles, when you have 4 hydrogens single bonded, that's actually the bond angles they end up taking. And if we wanted to see this structure with all of the hydrogens, this is actually what it would end up looking like. So you get kind of that straight chain, but if you were to look at it sideways, you get that little zigzag pattern, and there's 4 bonds connected to each hydrogen. And this would be our structure for butane. So this is what it's going to look like and all the ways we can draw it. Let's take a look at our next example. All right, so in our next example, what we're dealing with is we're going to find those same things, but we're given the molecular formula, and the molecular formula is C3H8. So we're going to have 3 carbons all attached, single bonded. The reason I know that is because that's all we're working with at the moment. Later on, that may not be so clear. But for now, it's good enough. So we're going to fill in all of the bonds. And since there's no other information and we need to have 8 hydrogens, we surround those carbons with 4 bonds each, and we end up with 8 hydrogens. Condensed formula, so CH3, carbon with 3 hydrogens attached. CH2, carbon with 2 hydrogens attached. And then CH3, carbon with 3 hydrogens attached. Stick formula is going to be 1 carbon, 2 carbons, 3 carbons. So there's a carbon here, carbon here, carbon here. And that's all you do. The name for this, now we have 3 carbons, so the prefix we would use is prop. And since there's only single bonds in between the carbons, we use the suffix ane. And that's all there is to that one. So we're dealing with propane, which is C3H8, 3 carbons, all single bonded. Okay, so now that we've done that one, let's do one more example just to make sure this is really clear. Okay, so this time we're going to do the same thing, but we're dealing with this compound down here. This compound is only drawn in the stick formula. So the first thing I would do is maybe we want to turn this into our structural formula. Maybe we could even find the name. You know what? Let's find the name first. We have, let's count up our carbons. 1, 2, 3, 4, 5, 6. 6 carbons gets the prefix hex. They are all single bonded because there's only a single line drawn between each carbon. So that means we use the ending ane, and this is a molecule called hexane. Now, structural or display formula, so 6 carbons, all drawn in a row, separated by single bonds. And everything else is going to be filled out with hydrogens. So, we need an H, 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 and then on the top. And now you kind of see why when molecules get larger, this is not always something you want to be drawing, which is why we tend to write this one. Now, our molecular formula, we have 6 carbons, so C6. Count up your hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So C14. Our condensed formula, CH3 for this one, CH2, 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 CH3. Okay? And that's our structural, or our condensed structural formula. One thing I do want to point out, for every alkane, they always have the molecular formula CnH2n plus 2. So what that means is however many carbons there are twice as many hydrogens plus 2, which hopefully makes sense because if we count up our carbons, we have 1, 2, 3, 4, 5, and 6. Each of them has 2 carbons attached, top and bottom, plus you have the carbons at the ends, which is why we have the plus 2. So this is the way that we are naming our alkanes when it just comes to things that are just straight chains. We count the longest chain of carbons, use the proper prefix. Single bonds tell us ane ending. Hopefully this helps, and I'll see you next time.